Now, we are starting chapter 7, our last final little chapter in AP Calculus AB. 7.1 is really just the area between two curves. And probably because so far we've already talked about if I just have a function f of x and I want to know the area from a to b of f of x dx, we know it is the definite integral from a to b of f of x dx. Now, the idea behind this, a definite integral is a summation, okay? The limit is either n approaches infinity or delta x approaches 0, okay, of the summation of these little bitty rectangles, the Riemann sums, right? Remember, the delta x is right there, and that is an f of one of those functions, times the delta x, the y value, and starting off at 1, going to n, and essentially we sum up an infinite number of those little rectangles, and that is what the definite integral actually is. That's one of those concepts. It's hard because we don't really do a lot of fleshing out of those Riemann sums and, actually finding, using summation formulas and stuff. But that is what is going on behind the scenes. So, in general, if I have this f of x graph and this g of x graph or function, and I want to find just the area between those two curves, it may be intuitive to you, and understandably so, if we have at least where they intersect. I mean, the idea could be that you just say, well, I could take that whole area from a to b of the top one is f of x dx. That will give me this entire area down to the x-axis from the top all the way down to the bottom, and then say, well, then I could just subtract out the area for the g of x. Try to do that in a little different color. That would be just this shaded region. And so what would be left over would be the area between the curves. And your thought process would be correct. And can I show you that it would be correct no matter where those functions are located? If the f of x1 is on top and the g of x1 is on bottom. So if that's our a and that's our b value, then even if it's below this x-axis, see, if I take the integral from a to b of f of x dx, which will, by the way, be a negative number, but then I'm going to subtract the integral from a to b, and by the way, this area would be shaded in blue, so it would just be above that curve, right? Shaded in blue. And then if I subtracted out the bottom one, g of x, which would be shaded in red, the whole area, right? And it would be a negative number. It would be a smaller negative number minus a bigger negative number, and so this area would in fact show up. This would be our red area, and the area between the two curves would show up, whether we're above the x-axis or below, or whether there's a mixture. It really doesn't matter. That would work. But I will show you kind of the better way to think of it if we have this random f of x function and g of x function. The way that we can and possibly should think of it, since we are trying to find the area between the two curves, we could actually just think of those little Riemann rectangles, and the width of it is a dx, right? And the height of each of those would be the top value minus the bottom value, right? At that particular x value, right? But again, if we take an infinite number of those little rectangles, sum them all up, we are actually taking an integral, and of course we would need those x values going from a to b. And this would be the quicker way and nicer way to set up that value. Since I'm just looking in terms of generalities on this one, this works even if we have like functions that cross more than once. The issue here, though, is we would have to split it up. This would be our A, B, and C values. And so the area between F and G, this red area, would actually be the integral from A to B of, I call this a little representative rectangle. It's never a bad idea to draw one, understanding the width is a delta x or a dx, and just follow the top one is from our f function, right? And the bottom one is from the g function, and so top minus bottom times the width, dx delta x. Then we would simply add it to the blue area, then would be a representative rectangle here would be an integral from b to c, but the top one is actually g of x, and the bottom one is the f of x. So this would be the setup for doing these by hand. Interestingly enough, if it's a calculator problem, what we can do is just go A to C, and it really doesn't matter which one you put on top. Throw it in an absolute value, and it will give you that exact area. So understand, calculators make this beautiful, but non-calculator is not horrible. So let's just look at a couple of examples. I'm going to pull out the old graph paper, hoping to make our problems a little bit neater. So let's look at f of x equals x squared plus 2x plus 1, g of x equals 2x plus 5. I'm going to take my easier one to graph here. It's just a line, right? Y equals mx plus b. 1, 2, 3, 4, 5. Y-intercept, rise 2, run 1, down 2, over 1. Got a good little line here, right? Alright. Now, this one, I'm going to use a little bit of calculus. It is a parabola, but remember, where the derivative equals 0 is where the vertex is, right? So 2x equals negative 2. X equals negative 1 is actually where the vertex is. And the y value would be 1 minus 2. Negative 1 plus 1 would be 0. So negative 1, 0. And the a is just right 1, left 1, up 1. So it's looking like down 2 over 1. Looks like I see one intersection point. 1, 2, 3, 4. And I will finish it in a minute.